Okay, everyone. In this video, we'll go over, BFS and DFS, and sort of kind of walk through an example problem together. Before we start, just a reminder, we have this new idea of graph. Essentially, graph consists of, some sort of vertex and some sort of edge that indicates like I'm connected to some other vertex, essentially. And I guess why are we studying BFS and DFS in the first place? Well, if you go back to 143, right? When we first learned about trees, the first thing we learned about is how we traverse through the tree. And we learned that in tree structure, we could either use pre-order, in-order, or post-order traversal. And how I like to think about it is BFS and DFS is just another way of its way of kind of traversing through a given graph, essentially. So given a graph, like how do we traverse through a graph? Well, there's BFS and DFS. So it's just two different types of ways to kind of like traverse through a graph, essentially. All right, so now that I've kind of talked about the BFS and DFS, let's sort of talk about the pseudocode of BFS and DFS. So I'm just going to talk about the BFS pseudocode first, and we'll talk about the DFS pseudocode. And so in a BFS pseudocode, we're actually given a graph because we have to, like I said, BFS is a traversal of graph, essentially. And we have to be given a vertex of start, essentially. And this vertex of start, what it allows us to do is that it allows us to actually sort of like have like a starting point of where we want to traverse first. Like the starting point of our traversal, essentially. Right? And so in BFS, we have to keep track of Q vertex parameter. And this basically keeps track of like the things we have to visit in our vertex. And then another thing we have to kind of like keep track of is set of vertex called discovered, new set. And this is super important, and I'll talk about an example of later in the video on why this is important. But for now, what this keeps track of is all the vertexes that that the BFS traversal has, kind of like discovered so far, essentially. And what we're gonna do is that in our queue and discovered, first thing we're gonna do is that, well, we discovered start vertex, so we're gonna add it to our discovered. And the next thing we're gonna do is that we're gonna add it to our parameter, our queue. We're gonna add the start vertex to our queue. And what this is gonna do is that it's gonna have a chain reaction, essentially. How I like to think about it is that, for instance, let's say S, starting vertex for 0, was our vertex 0, essentially. And it's gonna, after we have first added their start, we can see that like it's what BFS is gonna do is that it's gonna start a chain reaction of adding its neighbor, which is 1. And after we remove 1 from our BFS, it's gonna, add 2, 4 into the queue, essentially. So it's like, kind of like a chain reaction in a way that like it visits all the node, essentially. So this starting vertex is kind of important into implementing our BFS. Without the starting node, like we don't know where to start, essentially, right? And so what we're gonna do is that we're gonna remove the very first thing in our queue, and within that vertex, we're gonna check all of its edges or all of its neighbors, essentially, and say, hey, have you been discovered before? If you haven't, then add it to our queue and add that newly discovered one in, vertex into our discovered set, essentially. So let's do like a quick run through, I guess like a small example of that pseudocode I just talked about. So, yeah. So let's say we're given a graph with A, B, C, like that. And let's say I want to run through BFS on this. So BFS keeps track of Q, and we'll call this front. And we'll also keep track with, discovered set of discovered vertexes so far. All right, so, and let's assume that A is our starting point. All right, so A, essentially, we're gonna add our starting vertex first before we go into the while loop. And so A is gonna be in our queue, and it's gonna be discovered in there. And we're gonna check after we have done so. We're gonna enter this while loop essentially. Basically the while loop is saying while my queue is not empty. Well, in this case, right? While my queue is not empty, I want to keep on doing this loop, and it seems like my queue is not empty. So while my queue is not empty, I'm going to remove the very first thing from my queue. Well, A is going to get removed, and for all of the removed removed vertexes neighbors, we're going to add it into our queue only if they're not discovered yet. And so what I mean by that is we know that after we have removed A, we're going to check its neighbors, B and C, and ask, hey, B, have you been discovered yet? Well, in this case, B is not in our discovered set, so we can safely add it into our B. And then we're going to ask the same thing, hey, C, have you been discovered yet? Well, C is not been discovered yet, so we'll add it into our C. And every time we discover a new one, new vertex, we have to add it into our discovered essentially. So B and C will be in there in our set again too. And so the question is like, what if we didn't have this discovered set? Right? So let's say we didn't have this discovered set at all, right? And let's say we're at this state of our traversal where we have added B and C in there, right? So the next thing we're gonna do in our queue is that if we were to remove B in there, the question is, do we add A and C in there again? Right? I mean, they've been discovered before in our previous drawing because we kept track of it. But if we didn't, right, we would eventually have to add A and C in there, right? And we can see that one problem I already see that is that we're traversing through the same vertex, again twice essentially, and we don't want to do that in our traversal. Like you can think of it as like in tree traversal, we never actually visited or done some work in a tree, like a certain node twice, essentially. And so if I were to remove C, do I have to add B and A and B in there? Well, why not? Like, let's add A and B in there because we're not keeping track of discovered, right? And so now, like, let's say I removed A in there again, like I'll have to add B and C again, right? And so forth on. Like we can see that this queue just grows on, and we're actually never gonna end this while loop because queue is never empty essentially. So this is why having a set of discovered is very, very important. Yeah, this word must be important. Sorry, my handwriting's really bad right now. Still getting used to this drawing tablet. All right. So now that you got sort of like a high overview of how BFS traversal works, well, let's talk about DFS then. Well, what is the difference between BFS and DFS? Well, if BFS used a queue to kind of go over it, well, the only difference between BFS and DFS is that if BFS used queue, well, DFS is just going to use stack. That's it. Nothing else, like no other magic. And why, like you might ask, why is this giving us different traversal? Well, I kind of mentioned it before, but BFS is FIFO, and then DFS is LIFO structure. And because we're basically like adding and removing in a different ordering, it's gonna allow us to traverse to our basically graph in different ordering too, essentially. Yeah. So other than that, why don't we try, running through an example of, BFS and DFS. Actually, let's just run through BFS. Example of BFS. I think DFS is like simple as long as you get BFS, because the only difference is stack, right? So let's just go over BFS traversal in this case. And there could be multiple answers to this, and I'll explain why. But for now, let's just kind of go over this. So we know that for BFS, the first thing we have to do is that we have to keep track of the queue, so called parameter. And our front of our parameter, our queue will be like this, and this will be our back. And we'll also keep track of discovered so far. All right. And yeah, and that should be the two things we want to keep track of in BFS. And we'll also have like the notion of like order visited essentially. I'm not keeping track of it, but if I were to like, I just want to show you like the order of visiting in our BFS. So BFS, what we do is that we first add our starting vertex, and we'll assume that A is our start. Okay. Actually, before I go over this problem, I guess you can pause the video, try this on your own, and I'll give around 2 seconds before I start explaining this. Okay, welcome back everyone. Hopefully you have paused the video and tried this on your own. If not, it's also fine. But what we do is that we first add our starting vertex, which is A essentially. And every time we discover new node, we basically have to add it to our into our discovered set. So we'll add A in there. And the first thing we're gonna do is that while my queue is not empty, right? I'm gonna remove the very thing in front of the very front of the queue vertex. In this case, it'll be A, right? So we remove A from our queue and then ask its basically go through all of its neighbors and essentially see if they should be added into our queue or not. And well, it's sort of arbitrary in the sense of like I can add into C, B, F, G, or G, F, B, C. Well, it doesn't matter which order you go into, as long as yeah, it depends on the implementation. But for now, I'm just gonna say F gets visited, G gets visited next, and then C gets visited next, and then B gets visited next in our for loop essentially. And I guess so. In terms of mechanical problem, there could be multiple answers to this. And so, like I said, I'm just gonna add F in there. And before I add F, I guess, well, if we go through this for loop, right, essentially, to check its neighbors and ask, hey, F, have you been discovered before? Well, in this case, F's never been in our set of discovered yet, right? So because of that, well, F's never been discovered before. So F could be safely gone into our queue. And then because of that, we have, just discovered F, we have to add it into our discovered. And then now we ask G, hey, G, have you been discovered yet? Well, G's not in our discovered. So we'll add G into our discovered set, and we'll add G into our queue. And we ask the same question for B and C, and we can see that B and C is not yet discovered yet. So we'll add B and C in there, and we'll add B and C into our queue too. All right, so let's keep on moving forward onto this example. So now F gets removed from our queue since it is the very first front thing in our queue. And we ask the neighbors of F, A, and H whether or not if they haven't discovered yet. And if they haven't discovered yet, we can add it, update into our queue and discovered set. And first thing I'm gonna ask is, hey, A, have you been discovered yet? Well, A has been discovered, so we cannot add it into our BF in our queue. And yeah, then because of that, we're just gonna ignore A in this case. And so we're gonna ask H, hey, H, have you been discovered yet? Well, H has never been discovered yet, right? So we're gonna actually add H in there. And we're also just, discovered H, so we'll put it H as discovered in there. And order visited is actually A and F so far. And so F doesn't have any more neighbors, so we're done with F's neighbor. So now we're going to remove the very next thing in our queue, which is G essentially. And so I'll update my order visited into G. And we'll ask G's neighbor, A and H, hey, have you been discovered? Well, A and H has been discovered before, so we're not going to add it into our queue. So and we'll move on to the next node essentially in our queue. So we can see that B is going to get removed. And because B's only neighbor is A and A has been discovered so far, before, so we don't have to add A, and then we can just move forward. And we have just visited B, and then next node we're going to visit is C. So order visit is C, and then we're going to ask C's neighbor E and D, hey, have you been discovered yet? Well, E's never been discovered before, so we'll add into our E discovered E into discovered, and we'll add E into our Q. And we ask the same thing, hey, D, have you been discovered yet? Well, D's never been discovered yet too, so we'll add D into our discovered and D into our Q. All right, and we ask C, A, the same question, hey, have you been discovered yet? And well, A has been discovered, so we don't add it to our Q. Okay. And we can kind of see how discovered thing is super important. Right? It gets used often too. All right, so next thing is H gets removed from our Q. And we ask H's neighbor, which is F and G, hey, have you been discovered yet? F and G, we have been discovered before, so we don't add into our Q. All right, and then so we can move forward. And E, basically, it asks us neighbor C, hey, have you been discovered yet? Well, C has been discovered before, so we can say, well, E doesn't have anything, there's no neighbors for E to add, so we don't have to update anything in our discovered queue. And same thing with their D. So next thing we're going to visit is D. So we'll add D into our order visited. And D is going to ask us neighbor C, hey, C, have you been visited yet? Well, C, we can see that it has been discovered before. So because of that, we don't have to add it to our queue. And because now our queue is empty, we're done. We have gone through our BFS in ordering A, F, G, B, C, A, G, D. And this isn't like the final, this isn't the only, like I said, this isn't the only way to visit your, graph and BFS ordering. There could be multiple ways. But I want to show you one thing, though, of how BFS is kind of cool in a way. So we started with A, essentially, right? And we can see that the next order visited was FGB. Well, it's F, G, B, and C. And the next set of nodes that we visit is EHD, on the HED. So it becomes HED, something like that, right? And we can see that right here, like BFS actually, if we were to use BFS, it actually goes by level, right? And this is kind of cool in a way that like, there could be many applications to this depending on different traversal. So actually, I wanted to try to use DFS to go over this problem, but it seems like this video is too long. But if you were to try DFS though, you'll notice that if I were to draw DFS in terms of how they traverse it, and let's say like it'll actually visit. Let's say I visited F node first, then it'll visit H node, G node first. It'll be it'll traverse the first like one part of the graph first, and then let's say I added B next, and then it'll travel this node, this set of nodes first, and then if I were to add C next, it'll actually add these set of nodes too. So we can see that like for DFS, which is same thing as depth first search, we can see that once it adds like some node, it'll actually go in depth in terms of like going, traversing through essentially. So try DFS on your own and see, and kind of draw this kind of visual representation and see how BFS differs from that. Other than that, thank you.